Let's talk about some of the different intermolecular forces that you might find in molecules and use them to describe some of the properties that they might have. Present in all these different molecules, and you can use them to describe why condensed phases exist in the first place. And the strength of these forces can vary depending on how, the composition of the molecules and what they're made out of. And so it might depend on things like electrostatics, right? How much of a difference is there between the polar, non-polar parts of this positive and negative charges. It might depend on the size of the molecule, right? How big the thing is. And it might depend on the shape of the molecule, what it looks like in 3D space. And the way we're going to use these trends is to try to predict stabilities. And we're going to infer stability by things like melting points and boiling points. Okay, so the first intermolecular force that we're going to talk about is something called the van der Waals force. And van der Waals forces are typically the weakest intermolecular forces. So these are due to what's called the dispersion force between an instantaneous dipole and an induced dipole. Okay. What exactly are instantaneous dipoles and induced dipoles? Well, I'll show you a picture in a minute, but before I do, I just want to use the word polarizability to throw it at you. Okay, polarizability has to do with how the electron density within an atom or molecule gets distorted or affected by the presence of some kind of external magnetic field. Okay, and so basically, as the size of the atom or the molecule increases, meaning how many electrons you have, the magnitude of this polarizability also goes up. So the more polarizable things tend to be larger as well. Okay, and so here's an example of what this looks like. Let's pretend that you had two atoms or molecules here. Okay, and so here's one, and here's another one. And in general, they might be different shapes, but we'll assume that they look like spheres. Okay. As I bring them closer and closer together, right, so this one goes this way, and this one goes this way, all of the electrons that are on the outside over here are being attracted to the nucleus over here. And so that causes it to get together and distort. Okay, and so all of the electrons get repelled so that there's a buildup of negative charge on the left side. So this becomes delta negative or partially negative. And this side where the nucleus is, or lack of electrons, becomes partially positive. However, there's nothing special about the atom or the molecule on the left. Same exact thing happens to the atom or the molecule on the right. So I get this other distribution of charges so that this side becomes positive and negative, and they get complementary. Okay. So you can see here that the partially negative part gets attracted to the partially positive part, and vice versa. Okay, so these are the dispersion or van der Waals forces. The shape of the molecule can also affect how strong these forces are. Okay, so as a general rule of thumb, the more stretched out or elongated the molecule is, the stronger these forces are going to be, or the magnitude of these forces increases. And we attribute this to a greater dispersion between them. Okay, so here's an example. Let's look at two isomers of things that are called alkanes. Okay, so here's octane, which has 8 carbons in it and 18 hydrogens in it. And you can see the structural formula for octane down here. Okay, so each of these points is a carbon atom, and each of these carbons is connected to a certain number of hydrogens. Right now it doesn't really matter, but all of the ones at the ends have 3 hydrogens, and all of the ones in the middle have 2 hydrogens. Okay, down here is a ball and stick space-filling model of what this looks like. Okay, and so all of the dark gray represents all the carbon atoms, and all the white or light gray represents all of the hydrogens. And the point is that this is meant to show you what a 3D model of octane looks like. Basically a long rod. Okay. So the melting point for octane is about negative 56.8 degrees Celsius, And the boiling point for octane is about 125.7 degrees Celsius. Those are just numbers. Now let's look at iso-octane, which is an isomer of octane. Okay, it has the same exact molecular formula, still has 8 carbons and 18 hydrogens, but now the structural formula is different, how the bonds are connected to each other, or how the atoms are connected to each other with these bonds. Okay, and so here are my 8 carbons, and all the carbons have the requisite number of hydrogen atoms, but the point is that the shape of the molecule is now very different. It looks more compact and spherical and almost like a ball, okay? And so here's the argument, okay? If I have something like this, like octane, where it's a very long, elongated shape, I'm just going to draw it here on the side, okay? And I have another octane nearby that's also very long and elongated. There's a lot of surface area for them to come into contact with each other and be attracted to each other and exert these dispersion forces. Whereas if I had things that were more spherical, there's less dispersion going on because there's less surface area for these things to get in contact with each other. So if I have less dispersion, less surface area, less polarizability, fewer intermolecular forces, probably going to be weaker and not as stable. And so if it's weaker and not as stable, I would expect the boiling points and the melting points to also be lower. And you can see that here, right? For octane, the boiling point, the melting point is negative 56.8, but for iso-octane, the melting point actually went down by almost 50 degrees, right? Negative 104.7 degrees Celsius. And for the boiling point, it also went down from 125.7 to just below 100, 189.2. And so even though these molecules have the same atoms with the same kinds of bonds and the same kinds of dipole moments, and they're both nonpolar, they have very different physical properties because of these different dispersion forces.